Hello friends, welcome to the diffusivity and solubility of the gases in polymers under the edges of mass transfer phenomena in polymers. In previous lecture, we discussed about the mass transfer coefficient in the laminar flow. We discussed about the mass transfer in the falling film. Had briefly described about the laminar falling film in inclined surface where we use the angle theta. We described about the mass transfer coefficient in the turbulent flow. We discussed about the boundary layer theory concept and the film theory concept. In this particular segment, we are going to discuss about the diffusion aspects in polymers. We will discuss about the gas diffusivities in molten polymer. We will describe about the gas solubility in the molten polymer with certain examples. Now, usually we will go for different laws which we studied in previous chapters. So, when we talk about the diffusion and a solution in the polymers, this is a very integral part of different type of aspects, and especially when we try to synthesize the specialty polymers. Now, in this aspect, the Fick's first law gives the simplest representation of the molecular diffusion of a species in a system. Now, this expression relates the molar flux Ja of species A to a gradient dCA over dy by means of a transport or diffusion coefficient dAb. So, this can be represented as Ja, this is the molar flux, is equal to minus dAb dCA over dy, where dAb is a property of the system in much of the same way, and that the thermal conductivity is for the transfer of heat. Now, diffusivity is the ratio of molar flux to concentration gradient, whereas the thermal conductivity is the ratio of the heat flux to temperature gradient. Now, for diffusion of a molecules into a liquid, semi-solid or solid system, there is an important limiting case which is solution. The analogy to this particular situation is a chemical reaction, which is a kinetic process, and that is ultimately limited by the chemical equilibrium. So, all these things are very important in this particular aspect. Now, both the diffusivities and solubilities of small molecules are important in polymer processing operation, and the rate of transport of small molecules within the polymer being processed, which is related to the diffusivity, and solubility can be fixed or can fix the retention of molecules in the system for a given temperature and pressure. A third coefficient, this is some importance that is called the permeability, which is defined as the amount of a diffusing molecule that passes through a polymer film or a unit thickness per second per unit area and a unit difference of pressure. So, the diffusivity, solubility and permeability, they are related by this particular equation, that is P is equal to D into H, where D is the diffusivity and H is the Henry's law constant. This can be obtained from this particular relationship, that is HPI is equal to Xi, where Pi is the partial pressure of the diffusing component and X is the gas concentration in the polymer. Another thing is that this permeability apply mainly to the molecule transport in the solid polymer, particularly polymer films, and diffusivities are usually obtained in conjunction with the permeability measurements. So, the principal role of processing with respect to the permeability and diffusivity in the solid polymer is usually developed for the material structure characteristics and mass transport of gaseous molecule in molten or thermally softened polymer system is a particularly pertinent area, and this is so because the polymer processing operation generally involve gases diffusion system. Now, if we talk about the measurement of solubilities and diffusivities, they have been accomplished by the various techniques which we have represented over here, like the methods. There are different methods for measurement, like movement of a color boundary. If we can use it for diffusivity as well as we can use for the solubilities, and a gas chromatography we can use for the diffusivity, but we cannot use for the solubility. Apart from this, the piezoelectric, which can be used for the both the purpose, and special diffusion cells, again it can be utilized for the both diffusivity and solubility. Now, usually when we talk about the gas diffusivity in the polymer system, there is some sort of experimental demonstration. So, a listing of experimentally determined diffusivities for a variety of gases and a polymer is given in this particular table at a given temperature of 188 degrees Celsius. Here, these are the various gases which can be utilized in several times with respect to the polymeric system. And there are so many polymeric systems like polyethylene, polypropylene, polystyrene. So, we have enlisted helium, argon, methane, nitrogen, carbon dioxide. So, all the diffusivities is given with respect to three different polymer matrix: polyethylene, polypropylene and polystyrene. Now, the diffusivities of the gas in polymers, these are related to a variety of parameters like temperature, pressure, the nature of gases and the nature of polymer. Now, in order to deal properly with the processing operation, it is necessary to be able to take these parameters into account, which means that correlations are needed, because some of things you can measure directly and some of things you need to have some correlations so that we can establish the complete profile. So, diffusivities, this can be related to the temperature by an exponential function, and that is equal to D is equal to D naught exponential minus ED over RT, where ED is the activation energy of a diffusion, which is usually represented in kilocalorie per mole, and D naught is the pre-exponential function. This is an empirical constant and is having the units of centimeters square per second. So, if we take the things into consideration, then experimentally determined values of ED and D naught is given in this particular table for the different polymer matrix like polyethylene, polypropylene, polystyrene, and we used different gases like nitrogen, carbon dioxide with respect to the polypropylene, and then polystyrene, hydrogen, nitrogen, methane, all these things. So, ED in kilocalorie per mole and D naught and at a given temperature, because temperature plays a very vital role. Now, if we talk about the various values of ED and D naught, this can be estimated for other gases too and the polymers by using these two figures. This is the logarithmic of D naught versus activation energy divided by gas constant, and this is the logarithmic of D naught versus activation energy divided by the gas constant. So, all these things can be utilized. Now, in this particular figure, figure 1, the logarithmic of D naught is plotted against ED over R, and this particular plot, this gives the plot of ED versus the function of polymer's gas temperature and epsilon over K, a gas molecule parameter. Now, in order to use the data of these two figures, figure 1 and figure 2, first establish the ED value from this figure number 2 for a given polymer by using the polymer's glass transition temperature and epsilon over K for the gas. Next, to obtain the D naught value from this figure number 1. So, the polymeric the glass transition temperature and epsilon over K for the gas is used from the table, like we have enlisted different gases like hydrogen, helium, nitrogen, carbon monoxide, carbon dioxide, methane, all these gases, and then a collision diameter which is given in the angstrom, which is given, and epsilon over K in Kelvin is also given. Now, the smaller the molecule, the larger the diffusivity. This becomes apparent when a parameter, that is the logarithmic of the diffusivity divided by the square of the diameter of the gas molecule. Now, the diffusivity decreases with increasing polymer weight, which is evident from the correlation and the plot. This is developed by Lindbergh in 1969. So, in this particular figure, we have represented the diffusivities of the gases versus polymer weight. Now, if we go for the explanation of this particular figure, the chain flexibility is not an appropriate explanation, as the glass transition temperature of the polyisobutylene lies between the polyethylene and polypropylene, whereas the correlation shows that polyisobutylene diffusivity data is to be lower than either of the two other polymers. Now, diffusivity is to be related directly to the mobility of the diffusing species, and the material could be arranged in order to increasing consistency or decreasing diffusing species mobility as a polyethylene, polypropylene, polyisobutylene and polyacetylene. Now, the relation this relation in this particular figure indicated that between the diffusivity and polymer weight, which is actually between the diffusivity and the mobility of the diffusing species, since these polymers, they differ structurally in pendant group attached to the basic polyethylene chain. Now, there are actually two relations between the diffusion coefficient and the reciprocal of absolute temperature. One of the relation that holds up to say 150 degrees Celsius, and second is in between 150 to 170 degrees Celsius. So, the resultant correlation, this involves the two complex equation with the diffusivity equation. In order to use the correlation, it is necessary to know the polymer density, the data as a function of temperature, the density data for the pure solvent as a function of temperature, several values of the polymer solvent system diffusivity for at least two temperatures, sorption equilibrium data for the polymer solvent system, rheological flow data for the polymer and solvent viscosity data. So, all these things are quite essential. Now, usually if we number them 1 to 6, these are then used to calculate the number of quantities such as solvent free volume parameters, a polymer free volume parameter and a molar volume at 0 Kelvin for the polymer and solvent. Now, these quantities are then used with the three continuity equation sets to calculate the diffusivity. Now, this method, this has been applied not to the semi-crystalline molten polymer like polyethylene, but rather to amorphous polymers too, like polystyrene and polymethyl methacrylate, and then which are the thermally softened. Now, it appears that the simpler generalized technique, they are adequate for the higher temperature range for both polystyrene and polyvinyl acetate PVA. Now, above say 420 Kelvin for polystyrene and 358 Kelvin for polyvinyl acetate. Now, these temperatures are respectively 1.1 and 1.2 times the polymer glass transition temperatures. Now, it is therefore suggested that the free volume model to be used in the region from the glass transition temperature up to 1.1 to 1.2 times of its value. Let us solve one problem, and that is what are the diffusivities at 220 degrees Celsius for the following system, like methane polyethylene, nitrogen polypropylene, krypton polyisobutylene. Now, given that D naught is equal to 2.2 into 10 to the power minus 5 centimeter square per second, ED, that is for the polyethylene, is equal to minus 3 kilocalorie per mole, ED for polypropylene 2.78 kilocalorie per mole, and polyisobutylene given as 5.4 kilocalorie per mole. So, putting these values in equation, which is D is equal to D naught exponential minus ED over RT. Now, D naught is equal to 2.2 into 10 to the power minus 5 centimeter square per second, and the ED values for polyethylene 3 kilocalorie per mole, ED for polypropylene 2.78 kilocalorie per mole, and ED for polyisobutylene, which is equal to 5.4 kilocalorie per mole, and T is given as 220 degrees Celsius, that is 493.16 Kelvin, and R is equal to 1.987 into 10 to the power minus 3 kilocalorie per mole Kelvin. See the consistency of the unit. Now, if we solve separately, then for the first system, methane polyethylene, the D is equal to 2.2 into 10 to the power minus 5 centimeter square per second into 3 into per 3 kilocalorie per mole over 1.987 into 10 to the power minus 3 mole into 493.16 Kelvin. Now this comes out to be D is equal to 6.7 into 10 to the power 5 centimeter square per second, and this is answer for the first segment. Now if we talk about nitrogen and polypropylene, D is equal to 2.2 into 10 to the power minus 5 centimeter square, 2.78, 1.987 into 10 to the power minus 3 into 493.16 Kelvin. So this comes out to be D is equal to 4.275 into 10 to the power 5 centimeter square per second. This is answer to the second segment. Now if we talk about the krypton polyiso, this is our third segment, that is krypton polyisobutylene, that is D is equal to 2.2 into 10 to the power minus 5 centimeter square per second into 5.4 kilocalorie per mole, 1.987 into 10 to the power minus 3 kilocalorie per mole Kelvin into 493.16, and then D comes out to be 10.69 into 10 to the power 5 centimeter square per second. This is our answer. Now let us take up another problem, that is you need to estimate a value of diffusivity for the system of carbon dioxide, polyvinyl chloride at 200 degrees Celsius, that is 473.16 Kelvin. Now it is given that ED for the polyvinyl chloride is 2.84 kilocalorie per mole and D naught at 461.16 is equal to 2.2 into 10 to the power minus 5 centimeter square per second. So let us solve this problem. Now we can establish the equation D at 473.16 Kelvin is equal to D 461.16 Kelvin, then exponential ED over R 461.16 Kelvin over minus ED over R 473.16 Kelvin. So this equation can be written as D 473.16 Kelvin is equal to 2.2 into 10 to the power minus 5 centimeter square minus ED over R into 473.16 minus 461.16 over 473.16 into 461.16. So if we solve, then it can become 473.16 Kelvin is equal to 2.38 into 10 to the power minus 5 cent, and this is our answer. Now let us talk about the limiting effect. Now the limiting effect of the diffusion of a gas into a molten or thermally softened polymer is its solution. Such behavior can be expressed in the form of Henry's law. Now, experimentally determine the values of H. The Henry's laws constant are given in this particular table. This table shows the Henry law constant for various gas polymer system, and usual units of Henry law constant is centimeter cube per gram atom. Now, here in this particular segment, you see that we have enlisted different polymers like polyethylene, polypropylene, polyisobutylene, polystyrene, polymethyl methacrylate, and then the different gases like nitrogen, carbon dioxide, argon, helium, all these things are enlisted and their respective Henry's law constant is being given in this particular table. Now, as with the diffusion, the solution is a function of a number of parameters including temperature, pressure and the nature of the gases and the polymer involved. So, the relation of Henry's law constant to a temperature is an exponential expression which is represented by H is equal to H naught exponential of minus ES over RT, where ES is the heat of a solution and which is having the units of a kilocalorie per mole. So, various experimental values being determined by the different scientists, and these some of the experimental values which are in use in the common polymers is given as polyethylene, polypropylene and polystyrene with respect to the different gases like hydrogen, carbon dioxide, nitrogen, methane, all these things. Now, it is evident from this particular table that the heat of a solution changes with the gas structure for a given polymer. Now, this phenomena usually was observed in a solid amorphous polyethylene and natural rubber, where the heats of solution move from endothermic to exothermic as the gas collision diameter increases. Now, in this particular figure, this demonstrates or compares the data for the molten polyethylene to data for solid amorphous polyethylene. Now, the dotted lines, this can be used to estimate the heats of solution for gases other than the nitrogen or carbon dioxide in the polyethylene. Now, references in this particular literature we have already included that Henry law constant is independent of pressure up to at least 1.01 into 10 to the power 7 Pascal and possibly up to 3.03 into 10 to the power 7 Pascal. So, in this particular figure where you see that heats of solution of a gas in the solid amorphous, that is the solid lines with circle, and polyethylene for the molten polyethylene, that is a dotted line, and we have represented the notation in triangle. Now, let us take up another problem, that is you need to calculate the Henry's law constant for nitrogen, helium, argon, carbon dioxide in solid amorphous polyethylene at 461.16 Kelvin. Here the H naught nitrogen is given as Henry's law, initial Henry law constant is given for nitrogen, helium, argon and carbon dioxide like 0.0351 to 0.0102, 0.878 centimeter cube per gram atmosphere and 3.384 centimeter cube per gram atmosphere. Apart from this, the ES values is given for nitrogen, helium, argon, carbon dioxide like this. So, we are having the equation with us like H is equal to H naught exponential minus ES over RT. Now, here R is equal to 1.987 into 10 to the power minus 3 kilocalorie per mole Kelvin. H naught for nitrogen is given, that is 0.0351 centimeter cube per gram atom. ES for nitrogen is given, that is 950 kilocalorie per mole. H naught for helium is 0.0102 centimeter cube per gram atmosphere. ES for helium 2300 kilocalorie per mole. H naught for argon 0.0878 centimeter cube. ES for argon 500 kilocalorie per mole. H naught for CO2 0.384 centimeter cube per atom, and ES for CO2 is equal to 800 kilocalorie per mole. So for nitrogen, H is equal to 0.0351 centimeter cube plus atom, 950 kilocalorie per mole, 1.987 into 10 to the power minus 3 kilocalorie per mole Kelvin, 461.16 Kelvin. Now this H is equal to 0.043 centimeter cube per gram atom. This is the answer to the first segment. For helium, H is equal to 0.0102 centimeter cube per gram, 2000 1.987 into 10 to the power minus 3 kilocalorie, 461.16 Kelvin. So if we calculate, then it comes out to be H is equal to 0.0619 centimeter cube per gram atom. So this is our answer. Now if we take for A, then H is equal to 0.0878 into 500 over 1.987 into 461.16. All other things are in their usual units. So H is comes out to be 0.118 centimeter cube per gram atom. This is our answer. Now if we talk about the carbon dioxide, so this is H is equal to 0.348 centimeter cube per gram atom into 800 kilocalorie per mole, 1.987 into 10 to the power minus 3 kilocalorie per mole Kelvin into 461.16 Kelvin. So if we calculate 0.417 centimeter cube per gram atom. So this is our answer to this particular segment. So dear friends, in this particular segment we discussed different aspects of mass transfer operation, and for your convenience we have enlisted different references and which are very useful for the future studies, and if you wish you can take the help of all these references. Thank you very much.